Welcome to David Alexander Maths Tuition. This is chapter 9F, where we are differentiating trigonometric functions. Okay, so just as we know that the derivative of sine x is cos x and the derivative of cos x is negative sine x, we need to remember that the derivative of tan x is sec squared x. So if y equals tan x, then dy by dx is sec squared x. So that's just one to remember. Again, it is given on the formula booklet in your exam. So what about the tan of 6x? Well, dy by dx is going to be the sec squared of 6x multiplied by the derivative of 6x, and the derivative of 6x is 6. So it's sec squared 6x multiplied by 6, in other words, 6 sec squared 6x. The tan of 3x squared would be sec squared 3x squared multiplied by the derivative of 3x squared, which is 6x. That would be 6x sec squared 3x squared. Okay, x squared tan 3x, well, we've got two functions here, so we're going to use the product rule. So we've got an x cubed and a tan 3x. So x cubed differentiates to 3x squared, tan 3x differentiates to 3 sec squared 3x. So top left, bottom right, that's going to be 3x cubed sec squared 3x plus 3x squared tan 3x. We could factorise out a 3x squared if you wanted to, but we could just leave it as it is. This last example, here we're going to use the quotient rule. So x squared tan of 7x, x squared goes to 2x, tan 7x goes to 7, sec squared 7x. So bottom left, top right. So that's going to be 2x tan 7x subtract top left, bottom right, 7x squared sec squared 7x all over the tan of 7x squared, or tan squared 7x. There we go. So you've been introduced to one new one already, which is that the derivative of tan x is sec squared x. For cot x, dy by dx is minus cosec squared x. For sec x, dy by dx is sec x tan x, and for cosec x, dy by dx is minus cosec x cot x. It all seems a bit weird at the beginning, but once you start using them regularly, you'll soon start to just know them all off by heart. But you don't need to know them off by heart as they are given to you in the exam. But if you have to look them up all the time, then maybe that's a signal that you just haven't done enough work on differentiation with trigonometric functions. After a while, they should start to sink. So here we've got y equals cot 3x. Well, the derivative of cot is minus cosec squared. So that's going to be minus cosec squared 3x multiplied by the derivative of 3x, which is 3. So that's going to be minus 3 cosec squared 3x. Sec squared x, okay, what's going on here? So remember that sec squared x can be written as the sec of x all squared. So we can do our usual, power comes down to the front, reduce the power by 1. So, okay, bit pointless writing a 1. And then what is the derivative of what's inside the brackets? Well, the derivative of sec x is a sec x tan x. So it's going to be another sec x as well as that tan x. So we've got sec x times a sec x. So dy by dx will be 2 sec squared x tan x. Cosec a half x. Cosec goes to negative cot. So that's going to be minus cot of 1 half x multiplied by the derivative of half x, which is a half. So minus a half cot 1 half x. Okay, so here we've got some interesting looking functions. So here we've got the product rule, we've got an x squared, and then we've got the cot of 7x plus 4. So x squared differentiates to 2x, and the cot of 7x plus 4, remember cot goes to negative cosec squared, so that's going to be minus cosec squared of 7x plus 4 multiplied by the derivative of what's inside the bracket, so minus 7. So now using the product rule, that is going to be minus 7x squared cosec squared 7x plus 4 plus 2x cot 7x plus 4. Okay, so here is another one. Again, we're going to use the product rule because we've got two functions here. We've got ln x and sec cubed x. So ln x differentiates to 1 over x, and sec cubed x, remember that can be written as sec x all cubed. That's going to be 3 lots of sec x squared multiplied by the derivative of sec x, which is sec x tan x. So what we've got in total is 3 sec cubed x tan x. Okay, so top left, bottom right, how are we going to write that? It doesn't really matter what order you put these functions in, by the way, but 3 ln x sec cubed x tan x plus sec cubed x all over x. Okay, sorry, that looks like a 3x. That was sec cubed x there. Okay, so probably need a little bit more space here, so I think I will just wipe the screen. Okay, that's a little bit better. So here we're going to use the quotient rule. So I've got 3 cosec 4x and I've got an e to the 7x. Now e to the 7x differentiates to e to the 7e to the 7x, nice and easy. Now cosec goes to minus cosec cot, so minus cosec 4x cot 4x, but there's going to be 3 lots of it because of that 3 there, but we're also going to be multiplying by the derivative of 4x, so it's not just 3, but it's 3 times 4, so 12. So using the quotient rule, we're going to chuck these two together. So I'd probably write this as minus 12e to the 7x cosec 4x cot 4x. Take away 3 times 7 is 21. So 21e to the 7x cosec 4x. And that is going to be all over e to the 7x all squared. There we go. And that is that. That's quite a tricky one, that one, but yeah, we are all done there. So just to run through everything from the beginning, just to clarify, so if y is sine x, then dy by dx is cos x. If y is cos x, then dy by dx is negative sine x. If y is tan x, then dy by dx is sec squared x. If y is cos x, then dy by dx is minus cosec x cot x. If y is sec x, then dy by dx is sec x tan x. And if y is cosec x, then dy by dx is minus cot squared x. So notice that any of these functions that begin with the letter c, the signs swap. I'm sure that's just a coincidence, but yeah, that's definitely worth remembering. Don't forget to swap the signs when you're differentiating a cos, a cot, or a cosec. Okay, so here is a bit of proof. This could be a question in an exam potentially. So show that if y is sec x, then dy dx is sec x tan x. Okay, so sec x is 1 over cos x, and that can be written as cos x to the power of minus 1. Okay, so if we're differentiating, so dy by dx is going to be power comes down to the front, reduce the power by 1, and then multiply by the derivative of what's in here, which is minus sine x. So we've got minus 1 times minus sine x, so those two negatives will cancel out. And what we can see here is that cos x to the negative 2 is 1 over cos squared x. So what we've got here is we've got a positive sine x on the top, and we've got cos squared x on the bottom. Okay, cos x to the negative 2 is cos squared x on the bottom. Now, what we can do is we can say that, well, sine x over cos squared x is sine x over cos x multiplied by another cos x. Now, sine x over divided by cos x, that is tan x. So we've got a tan x, and we've also got this cos x as a denominator, and cos as a denominator can become sec as a numerator. So there we've got it. We've got tan x sec x, or as they want as they want it, sec x tan x. So there we go. Okay, so here's another proof question. So what we are showing that cot x goes to negative cosec squared x. So we need to remember that cot x is cos x over sine x. So if I'm going to differentiate cos x over sine x, then I'm going to use the quotient rule. So that's cos x, sine x, cos goes to negative sine x and sine goes to cos x. So what we've got is minus sine squared x, take away cos squared x, all over sine squared x. Okay, so we know that sine squared plus cos squared equals 1. So therefore negative sine squared take away cos squared x is negative 1. So what this is minus 1 over sine squared x, and sine on the bottom can be cosec on the top, so that is negative cosec squared x, and that's what we were aiming for. Here's another one. If y is cosec x, prove that dy by dx is negative cosec x cot x. So the cosec x, that can be written as 1 over sine x, and that's the same as sine x to the power of minus 1. So let's differentiate sine x to the minus 1. So power comes down to the front, reduce the power by 1 and multiply by the derivative of what is in the brackets, which is cos x. So what I've got here is minus 1 cos x on top, or minus cos x, and this sine x to the negative 2, that at the moment is a numerator, but I can take it down to a denominator, and that is the same as sine x squared, or well, sine x, and I'll just write 2 sine x's. So sine x multiplied by sine x. Now, cos x over sine x is cot x, so this part is negative cot x, and a sine as a denominator, that is a cosec x. There we go. So I have shown it, although I've got it the other way around, but it doesn't really matter, which is the same as minus cosec x cot x, and that proof is complete. Okay, so to finish off this chapter, there's a couple of odd looking questions. Show that the derivative of arc sine x is 1 over the square root of 1 minus x squared. Now, it's a sort of question where you've probably got no idea where to start, and it all just seems a little bit weird really. So what we need to do is this. We just say that, well, let's say that y equals arc sine x. So y is arc sine x. So what this means is that the sine of y equals x. Okay. So here's a right angled triangle, and here's my angle y, and the sine of y is x. Now the sine of anything is the opposite over the hypotenuse. So to get x, that means this must be x and this must be 1. Let's just check that out. The sine of y is the opposite, which is x, divided by the hypotenuse, which is 1, and x over 1 is of course x. Now what is the adjacent side? So we can do Pythagoras. It's the square root of 1 squared minus x squared. So this side length here is 1 minus x squared square rooted. Okay, so if x is the sine of y, what I'm going to do is I'm going to differentiate, but here I'm going to do a dx by dy. Now the derivative of sine y is cos y, so therefore dx by dy is the cos of y, which is the square root. So remember the cos is adjacent over hypotenuse, 1 minus x squared all over 1, but we wanted dy by dx. So dy by dx is the dx by dy flipped, so that is 1 over the square root of 1 minus x squared, which is what we were aiming for. Here's another one where we're trying to show that the arc cos x is negative 1 over square root of 1 minus x squared, so I'll do the same thing. Y equals the arc cos x. I mean, if you prefer, you can write that as, that's what that means. So therefore the cos of y equals x. So if the cos of y, here's y, if the cos of y is x, then this must be x, this must be 1, so x over 1. And this side here is going to be the square root of 1 minus x squared. Okay, so if x equals cos y, then dx by dy is going to be negative sine y. So the sine of y is opposite over hypotenuse, 1 minus x squared all over 1. So if we want the negative sine y, then that's just the negative of the square root of 1 minus x squared over 1. So therefore dy by dx is therefore minus 1 over the square root of 1 minus x squared, which is what we were after. Okay, and finally show that the derivative of arc tan x is 1 over 1 plus x squared. Okay, so let's say y equals arc tan x, or y equals tan minus 1x. So therefore the tan of y equals x. So let's do our little triangle. Here is y, and if the tan of y, which is the opposite over the adjacent, is x, then this must be x, this must be 1. So the hypotenuse is the square root of 1 squared, which is 1 plus x squared. Okay, so if tan y equals x, or if x equals tan y, then dx by dy is sec squared y. So dx by dy, another way of, there's a few ways we can go from here, but I'll say it's 1 over cos squared y. So therefore dy by dx is cos squared y over 1. So just cos squared y. So what is the cos of y? The cos of y is 1 over the square root of 1 plus x squared. And if I want to square that, that is just going to be 1 over 1 plus x squared. There we go. So there I've shown that the derivative of arctan is the 1 over 1 plus x squared.